Okay, so we want to look a little bit at some of the homework set from 4.3 here. And so we want to look at number 11 and number 25. So I don't know that I necessarily need to share the screen with you guys. But number 11 just says we want to find a particular solution, excuse me, to x squared y double prime minus 3x y prime. Nope, I lied, it's plus 5. The wrong one. Plus 5xy prime plus 4y equals 1 over x cubed. Okay, let me go to the board here just so you guys can see that. All right, so there's a differential equation we want to solve. All right, so ideas, thoughts. What should we do first?
Divide everything by x squared.
I think that's absolutely the best first move. Let's just get it so that it's kind of in the form that we're used to. So we've got y double prime plus 5 over x times y prime plus 4 over x squared times y equals 1 over x to the 5th. All right. So what we want to do is see if we can come up with a particular solution. Now, if you think about what we did last time, it really was just a, let's make a best guess, right?
Best guess.
Let's just see what we think might work. All right, so looking at that one, what kind of form might we want? Nothing? How about let's go over the list of things we've tried before. So I think it's pretty clear we don't want exponentials, right? Because exponentials, their derivatives are more exponentials, and we're not going to just get 1 over x to the 5th. Sine and cosine we can probably throw out. Similar reason. What about polynomials?
A negative one?
Yeah.
I mean, are we, like,
Okay. I don't know what kind of weird feedback that was. Can you say that again, Ian?
x to the negative third or something?
Oh,
Oh, whoa, is it loud?
Now it's good again.
shit.
It was all like scratchy and. Okay, so if we think about a polynomial, the problem with a polynomial is, well, think about what we would need to get 1 over x to the 5. There's no way we could have a polynomial divided by at most x squared to give us that. But going with some sort of a x to the minus something may not be a bad idea. Because think about it, if we do an x to the minus, as we continue differentiating, it's going to be more negative, right? Like if we started with, say, an x to the minus 10, the next is x to the minus 11, then x to the minus 12. So there's a nice kind of pattern to that. So anyone have a suggestion of what power of x we should use? All right, so Ian's afraid to say it out loud. He just typed x to the minus 3. What do you guys think? Because if we use x to the minus 3, then what?
You just muted yourself.
I just noticed that. Let me actually go back to the other screen. Maybe it's my computer's being weird. It's taking Ian's voice. It's yelling at me. Okay, so let's try again. Oh, and now I'm back. But yeah, it's probably Mercury. Okay, so if we go with x to the minus 3, this first one will be x to the minus 5. Differentiate will give us x to the minus 4, which then with the x is another x to the minus 5. And the second derivative is x to the minus 5. So I definitely think let's try something of the form a x to the minus 3. So if we differentiate that, that'll be minus 3 ax to the minus 4. And then the second derivative will be 12 a times x to the minus 5. So let's put those into the derivatives, or into the differential equation. So we're going to get 12a x to the minus 5 minus 15a x to the minus 5 plus 4a x to the minus 5. And what we need that to be is 1 over x to the 5. So let's go ahead and combine those. 12 plus 4 is 16, minus 15 is just 1. So we're left with a single a x to the minus 5. We need that to equal 1 over x to the 5, which suggests a equals 1. So I think we got ourselves a particular solution, x to the minus 3. There you go.
Are we just supposed to find a particular solution to this, or
Yep, that's all this
so
one said.
not just a generalized solution?
Nope, it just says find a particular solution.
Wow, that's not that bad.
When all it is find a particular solution. That's all you got to do. So number 8 is actually really, really similar. You're going to have a different power of x over here, but it's the same kind of idea. So you guys are correct. I didn't show you any examples that had, some sort of an x to the minus. But you can see kind of why we went with that as the idea. So a lot of this, and I know that students in general don't like this kind of thing, but a lot of this is you have to look at it and then think about all the different kinds of functions and figure out which one is going to do what you need it to do. And in this case, our target was something that was x to the minus 3. All right, so okay for that one? All right, so number 25, let me pull that one up. Okay, so for 25, they actually tell us something. They tell us if omega is a constant, differentiating a linear combination of cosine of omega x and sine of omega x with respect to x yields another linear combination of cosine and sine. Right? So in this one, use this to find a particular solution of the equation. All right. So we're going to find a particular solution, and then it says find the general solution, and then we're indicated solve the initial value problem. So I picked the one that's not the initial value problem because the aforementioned laziness today. So, but this one we're going to go all the way. So we're not going to just find the particular, but we're going to use it. Let me just go ahead and get this written up here. All right. So we've got y double prime plus y prime equals minus 8 cosine of 2x plus 6 sine of 2x. So since we're going to go all the way, let's start by finding the fundamental set. So let's make our polynomial. So we're going to have r squared plus r equals 0, which of course factors to r times r plus 1. So that gives us y1 is equal to e to the minus t, and y2 is going to equal 1. So there's our fundamental set, e to the 0 and e to the minus 1. All right, so we'll slap that into the overall solution. But now let's go and find the particular solution. Now, that little statement they had in there about, if omega is the same, then differentiating, you get a different linear combination. That's what we already knew. We already knew that the goal for this kind of form is going to be some multiple of cosine. So we'll call that A times cosine of 2x plus some multiple of the sine. And so the question is, what are A and B? All right, so are we all okay with using this form? You got sine and cosine. You want to start with sine and cosine. All right, so we'll differentiate. So we got a negative 2a cosine plus, or sorry, negative 2a sine plus 2b cosine. And then differentiating one more time gives us a minus 4a cosine and then a minus 4b sine. Okay, so then according to the differential equation, we want to just add y double prime and y prime. So just take these two and add them. And I'm going to go ahead and combine the bits that have cosine and sine. So in terms of cosine, we're going to get 2b minus 4a. So that's the coefficients on cosine. And then on the sine, we have minus 2a minus 4b. And now we can create the system of equations because we know that 2b minus 4a has to equal negative 8. And minus 2a minus 4b has to equal 6. And those minus 8 and 6, those were the original coefficients up here. And now we get to solve. So let's see, if you multiply the first one by 2, the b's will cancel. We get minus 10a equals minus 10. So I think that gives us a equals 1. So
Let
then
me check that.
b is negative 2. And I officially beat Symbolab. I'll take great pride in it.
Not really. Apparently, after RREFing it, it's negative 7/2 and 1/4. Unless I entered that wrong.
I was about to say, you might want to check yourself.
Oh, shit. Damn it.
So, yes, I officially beat. All right, so A is 1, B is minus 2. All right, we're good.
Yeah, you're right.
Yeah, I know I'm right. Okay, so if we put those in, then here's what y is going to be. So we need our particular solution, which is going to be cosine of 2x minus 2 sine of 2x. And then we're going to take our fundamental set and multiply those by C1 and C2. And so it appears to me that there's the solution to this differential equation. So 28, I think, is kind of similar. It's just that time they give you some initial conditions. So obviously at this point, you would plug in and put in your initial condition. It also has something with the derivative. So you would put it into that as well. But that'll give you a system in terms of C1 and C2. And then just solve that system and you'll be good to go.
Should we also graph the thing like it says? Or do you know?
It says to graph it if it's an initial value problem. Because then you'll have your C1 and C2. And so you can just put that in and graph. Because the problem with like this one is, what does this look like? Oh, who the hell knows?
Yeah.
It totally depends on C1 and C2, and all kinds of different things can happen to it. I just realized this should be an X. See, it's not just the exam. So Trey, do I want you to draw a graph for the homework? I don't really care. I think it's probably a good idea to look at it just to get a feel for what's going on. You know, like if you look at this one, how about let's just look at this generically, depending on the C's. This cosine and sine bit, that's just going to be oscillating, right, as x goes on. The e to the minus x, that piece is just going to go away. So eventually, whatever that does to it is irrelevant. And then that C2, all that's going to do is just shift it up or down. So what this thing is going to look like long term is just whatever cosine of 2x minus 2 sine of 2x looks like. Just shift it up a bit or shift it down, depending upon what the C2 is. All right. So good for 25. And again, this had nothing to do with superpositioning. But the superpositioning, again, the whole idea there is if this had been, let's say, the minus 8 cosine 2x plus 6 sine of 2x plus 4e to the x. Okay, well, that just gives us another piece that we need to think about. But that 4e to the x, we would put a generic, let's say, c times e to the x and see what that forces that number to be. All right, so, okay for that? So just think about what we've been doing. It's all about trying to find that particular solution. And we're using the form of what we're looking at to find it. So if you were to kind of just make a list of what we've seen so far. Polynomials, guess a polynomial, right? Guess a polynomial of the same degree as your target. Sines and cosines, make your guess a combination of sine and cosine. Now, they do have to have the same omega in them. Like if we had cosine of 2x plus sine of 1x, our guess would actually be sine and cosine of 2x and sine and cosine of x. So we'd have to have 4 pieces. But for the sine and cosine, use those. For exponentials, use e to the same power. And we also now have seen that when we have x to the minus, we still use x to the minus as a guess. We just have to make sure that our last derivative is x to that negative power, right? So like that one where we ended up, we wanted it equaling 1 over x to the 5th. Our guess was actually 1 over x cubed.
just so that we get where we need to be. Okay, so that's where we are, and we're going to kind of continue doing this, but we need to talk about a specific situation, and let me show you what I'm talking about. Let me give you a differential equation here, and we're going to see if we can solve it.
Is this for section 5.4?
Yes, sir.
Cool.
This is 5.4. I guess. I don't know. It's the method of undetermined coefficients, which is what we actually have already started doing. The method of undetermined coefficients, think about the name. We have coefficients, we just don't know what they are yet. And that's kind of what we've been doing with our guesses for particular, right? It's like, well, what's A, what's B? I don't know, we'll find out. Right, so they're undetermined coefficients. I kind of lump all this stuff into one. I would say from 5.2 through 5.4 or something. So where exactly I am, I don't know that I can answer you, Thea, but yeah, somewhere in there. All right, but let's try this one. So let's go with y double prime plus 3y prime plus 2y equals 4e to the minus t. So looking at this, what would your guess be for the particular solution?
Something to the some constant times e to the minus t.
Okay, I love it. Let's go for it. So we're going to do y sub p equals, say, a e to the minus t. Right, because exponentials, they give us more exponentials as we differentiate. So let's try this out. So then y prime is going to be minus a e to the minus t. Y double prime is going to be a plus a e to the minus t. So let's put those in. So we're going to get a e to the minus t plus 3 times negative a e to the minus t plus 2 times a e to the minus t. And we need that to equal 4 e to the minus t. Well, it's about this point you start seeing why I brought this one up. What happens?
Everything falls apart.
Yeah, if we add all this up, we get 1a minus 3a plus 2a. That gives us 0 equals 4 e to the minus t, which is a very false statement. That can never actually equal 0. But those are not the same things, which means this guess for our y particular is no good. So that's when we curse, maybe under our breath or maybe just out loud. And we go, uh-oh. Okay, so it's obviously not as easy as what I hinted at last time. I was nice. I showed you examples last time that worked. Here's an example that doesn't work. So of course, that makes us have to start thinking, well, what do we do to actually make it work? Well, what do we do every time we run into something like this where we've got a form we want, but it's not quite right? What do we do? So Wes just said cry. Okay, that might be true. But what technique to solving these things do we try? Yeah, so Trey just put it multiply by mu. But let's multiply by an integrating factor. And let's see what that integrating factor is going to have to look like. Okay, so clearly ae to the minus t won't work, but let's try some sort of a mu times ae to the minus t. So I'm just going to alter this ever so slightly and put in a mu. Now that's going to change my derivatives because now I have to do the product rule. So we're going to get y prime is equal to mu prime ae to the minus t, and then minus mu a e to the minus t. And then y double prime, again, I got to use the product rule. So there's on the first piece, and then the second piece, I'm going to get another mu prime ae to the minus t, and then plus mu a e to the minus t. All right, so putting that back into the differential equation, I can combine these a little bit. So I'm going to get u double prime, or mu double prime, I mean. U or u, same difference. Minus 2 mu prime ae to the minus t plus mu a e to the minus t. That was my y double prime. My plus 3y prime is going to give me plus 3 mu prime e to the minus t minus 3 mu a e to the minus t. And then adding the original is going to give me a plus 2 mu a e to the minus t. So if I add those all together, I get mu double prime plus mu a e to the minus t, and all the rest is gone. And what I need, oh, that should be a mu prime, I apologize, is that this needs to equal 4e to the minus t. All right. Can you see from that what mu is going to have to equal? Or maybe more to the point, what mu prime is going to have to equal?
Is it x? Mu is going to have to equal x. Well, t technically, but
Okay, so no, you're right. If mu equals t, this will work. Because then mu prime is 1, mu double prime is 0. Right? Really, what this is saying is that mu prime times a is going to have to equal 4.
Mm-hmm.
Which would be mu prime equals 4 over a, which is a constant, which makes mu double prime equaling 0. So it does turn out that mu in this case is going to have to be linear. It's going to have to be some sort of a 4 over a times t plus c. Now, since we're finding a particular solution, I can pick my c to be whatever I want. So of course, I'm going to pick c to equal 0 just to make life easy. So if I do that, we're going to let mu equal 4 over a times t, which if I put in there for my form for y particular, I'm going to get y particular is equal to 4 times t e to the minus t. So let's just double check it. Let's make sure that it actually works. It should, right? The way that we developed it, it should work. So y prime is going to be 4e to the minus t minus 4t e to the minus t. Y double prime, that'll be a minus 4 e to the minus t minus 4 e to the minus t plus 4t e to the minus t. So we'll take that y prime, it's minus 8 e to the minus t plus 4t e to the minus t. We're going to add to it 3 times the y prime. So it's going to be 12 e to the minus t minus 12t e to the minus t. And then we're going to add 2 times the original, which is going to be an 8t e to the minus t. And notice that when we add those things up, these 3 give me 0, and I'm left with 4 e to the minus t. So we found it. We found a particular solution, which means now we're good if we want to actually write the whole solution. So before we go there, questions about what we just did? No, we good? Okay, so let's finish this off. Now that we've got our particular solution, let's actually put it together to get our y equals, which means we have to go back and actually find the fundamental set for the homogeneous. So this is going to be r squared plus 3r plus 2 equals 0, which is going to be r plus 2 times r plus 1, which gives us y1 is e to the minus 2t, and y2 is e to the minus t. So then our solution is going to be y equals c1 e to the minus 2t plus c2 e to the minus t plus 4t e to the minus t. So there's your general solution to that differential equation. All right. So, yay. It appears that sometimes we're going to have to find an integrating factor. What would be really nice is if we could recognize when that's going to happen. Because if we can recognize when it's going to happen, it's going to make it that much easier for us. And then even better would be if we could find a generic way of building it so that we don't have to do it the same way every single time. Well, let's start with the why did it show up here? Can anybody see why we ran into a problem when we just tried a e to the minus t? What is it about this one in particular that led to that being a problem? Well, if you want another hint, I want you to think about how I went about this. I didn't do it in the usual order that I do things. What's usually the very first thing I do when I do one of these?
Oh, you found the particulate first rather than the finding the generic part of it.
Yep, and that's absolutely true because normally I go and I build this polynomial and I go down and find those. Okay, but I didn't do it that time or this time. I don't know if that was enough of a hint for you. But look at our fundamental set. One of the elements in that fundamental set is e to the minus t, which was the same form that we were looking for a particular. But here's the problem. If I take that e to the minus t and I multiply by an a, that's just going to be another solution to the homogeneous. It can't help but give me 0. So that's why we needed to have an integrating factor. And that was because the goal, what we were looking for over here, had in it a multiple of one of the fundamental set, which immediately rules that out as a possible y particular. It just will not work. Okay, so that's how we're going to recognize whether or not we can actually do this. If we run into this problem where our particular answer is a linear combination of the fundamental set, we're going to have to do something different. Okay, so at least there's how you're going to recognize. So you should always start by solving the homogeneous and finding the particular, or sorry, the fundamental set. And then compare that against what our goal is for the particular. Okay, cool. So we've got that. Now I want you to notice that what happened was that we ended up just multiplying by t. And that's actually always the case. We're going to end up multiplying our original guess by t. So let me show you why. Let's go generically. And so here's what we're going to do. Let's just say that we've got some y double prime plus p of x times y prime plus q of x times y double prime, or sorry, y is equal to g of x. And what we're looking for here is a particular solution that looks like mu times g. So again, let's just go ahead and differentiate real fast. And then let's put this into the differential equation. So again, I'm going to kind of group these a bit. So we're going to have the u double prime g of x plus 2 times mu times g prime. Actually, I'm going to get lazy here. Let me just write g plus mu times g double prime. And then we're going to add to that the p of x times y. So that's going to give us mu prime times p times g. And then plus mu times p times g prime. And then when we go to the last term, multiplying that by the q, we're going to get plus mu times q times g. And these last three, what we know about those last three is that's going to add up to 0, because we're going under the assumption that g of x is in the fundamental set. Now, technically, g of x is a multiple or a linear combination of things that are in the fundamental set, which means that it's in the solution set to the homogeneous. In the language of linear algebra, it's in the space. It's in the solution space to the homogeneous. So all of that equals 0. So what we now have is u double prime times g plus 2g prime plus p of g times mu prime. And that's going to have to equal our g. Well, this can be reduced down to a first order. Do that little substitution, right? Say, call this w. If mu prime is w, then mu double prime is w prime, which means it's just a good old linear first order that we can solve. But what this does lead to is that the mu prime is constant. And if mu prime is constant, that means that mu is linear. So if we just do a few more steps on this, this forces mu to be linear. So not only do we now know when we need to do this, we know that if we need to do this, all we have to do is multiply by t. That's it. So let's try this with another one. And let's see how it goes here. So let's take the differential equation y double prime plus y equals 2 sine of t. All right, so start with homogeneous. So we'll go ahead and build our polynomial here. We got r squared plus 1 is equal to 0. So r is plus or minus I. So what are our fundamental set then? What do we get when we get complex numbers?
Isn't it e to the x times cosine of x plus sine of x, right? Well, I mean, in this case, right?
Okay, so in this
Or am
case,
I
there's a
tripping up?
sine, there's the sine and the cosine, but there's no e because there's no real part to this,
Oh, got it.
right? So
Yeah.
if there was a number here, like it had been 2
Mhm.
plus or minus I, then there would have been an e to the 2t.
Got it. Because that multiplied by into the e, causing it to become 1.
Yeah.
Got it.
So this is just going to be cosine of t and sine of t. All right. But we can immediately see that we've got an issue. Our goal, the 2 sine of t, is in the solution set to the homogeneous. So that means we can't use that as our particular. But what we're going to do is we're going to take what we would have used as our particular, which would have been a cosine of t plus b sine of t. But we're going to multiply that by t. Another thing I just want to mention real quick, because you may be wondering, okay, you just said mu has to be linear. How come you don't write, you know, some sort of like mt plus b? Why don't you do the whole line? So first of all, any kind of a multiplier on this just gets distributed through, would change those a and b by that factor, will account for that. But more importantly, why don't we put a plus b? Well, that part, when it distributes, just becomes some sort of a multiple of cosine and a multiple of sine, which we already know are just going to lead to 0. So we're not going to bother putting those in because it's like extra work for nothing. All right, so here's our guess then. Let's see if we can figure out the A's and B's. So y prime, well, it's going to be A cosine t plus B sine t plus t times minus A sine plus B cosine. And then y double prime, let's go do this again. Well, it's going to give us minus A sine plus B cosine. This piece is going to give us a minus A sine plus B cosine plus t times minus A cosine minus B sine. All right. Well, now let's just add y double prime and y, add the originals, and see what we're left with. So we're going to get, these two are the same. So we're going to get minus 2a sine of t plus 2b cosine of t. And then when I take this yp, that piece plus this piece actually equals 0. They're opposite signs. So this has to equal 2 sine of t. So that makes a equal minus 1, b equals 0. So we now have our particular solution, or a particular solution, let me say. So when I put this all together, I'm going to get y equals c1 cosine of t plus c2 sine of t. So the linear combination of our fundamental set minus t cosine of t, because we found that a was equal to minus 1 and b was equal to 0. All right, so what do you think?
Pretty cool. So I'm seeing sort of a similarity to whenever we'd get like repeated roots, we just tack on a t to the second term. I guess this is sort of along the same lines, but it's for the particulate.
Yeah, it's exactly the same idea. Yeah, it's exactly the same idea, where we're basically, you know, bumping it up. The fact that it ends up being multiplying by t is for the same reason. Because if you think about that repeated root, wasn't that kind of the same scenario? I mean, we had something that we saw already was part of the fundamental set.
Yeah.
And so we needed to create something else. Well, that's what we're doing here. We're starting with something, a particular that's in the fundamental set. So we multiply it by a t. All right, well, speaking of repeated roots, let's look at an example involving that, because we haven't done one of those yet, right? The first one we had 2 real roots. This one had 2 complex roots. But I do want to show you a repeated root because it changes things a little bit. It'll feel like it's different, but it really isn't different. So let's just go to a nice easy one of those, like y double prime minus 2y prime plus y equals, let's just go e to the t. All right. So start with the fundamental set. The fundamental set here we have r squared minus 2r plus 1 equals 0, which is r minus 1 quantity squared, which means y1 is going to be e to the t. And what's y2? What do we do when it's repeated?
It's
Tack on
t
a t.
e to the e.
You slap on a t, so it's going to be t e to the t. All right, so again, no big deal. That's what we do with those. But now let's go to our particular guess. So what we'd want to guess is e to the t. However, there's going to be a problem because e to the t is already in our fundamental set. So then what we'd want to do is slap on a t. But that too is a bit of a problem for the exact same reason, right? When we multiply by t, that's still in the fundamental set. So what are we going to do? It's so easy that it probably seems too obvious.
Multiply it by t.
Yeah, multiply it by t again. So this time, we're actually multiplying by t squared, not just by t. And we're multiplying by t squared because of the fact that it already showed up twice. Because if all we did was go with t e to the t, that's still a problem. So we're going to jump up to t squared. Let's put an a on here. So our particular guess is going to be a times t squared e to the t. So that's what I was saying. It feels like we're doing something different, but we're not. We're really just multiplying t by the bigger one, the one that's already had the t on it. So let's see what this does for us. So then y prime is going to be 2a t e to the t plus at squared e to the t. And then y double prime, that's going to be 2a e to the t plus 2at e to the t plus another 2at e to the t plus an at squared e to the t. So let's combine those according to our differential equation here. So we'll get our y double prime. So that'll be a 2a e to the t plus 4a t e to the t plus at squared e to the t. Then we're going to subtract 2 of the y primes. So it'll be minus 4at e to the t minus 2at squared e to the t. And then we're going to add to it the original at squared e to the t. So when we add all that up, we get 2a e to the t. Everything else is gone. And of course, what we need that to equal is 1 e to the t. So that tells us that a is equal to 1/2. So let's go ahead and finish this off. So we're left with y is equal to c1 e to the t plus c2 e to the t, or sorry, t e to the t, plus, now we've got 1/2 t squared e to the t. So the 2 from our fundamental set plus this particular that we just found. And this one, I just want to factor out the e to the t, just so you can kind of see what's going on here. So notice that this is just a quadratic times that e to the t. And it's a quadratic because we started with a linear, but then had to multiply by t so that we could get out of the solution space to the homogeneous. All right, so questions, thoughts, comments? All right, so this is the general process. Now, when we run into a situation where the form of our non-homogeneous, or yeah, our non-homogeneous, actually matches fundamental set to our homogeneous. I think I'm going to pause
for the day here. Because to be honest, I'm done with algebra. I'm bored with it. And this is really just a lot of algebra, right? But it's guessing your form. So what we'll do next time is we'll make it a little bit more complicated. Like what happens when you don't have just say sine and cosine, but you got sine times some exponential piece, or an exponential piece times a polynomial and all that. It's going to be more of the, here's the pattern, this is what you're looking for. But then we're going to turn our attention to another way of solving these that doesn't require us to make a guess. And you can see why that might be the drawback to this method, is you have to have a really good guess of what kind of function is going to give you that derivative, right? Like what if it was this exact same one, but instead of equaling e to the t, it equaled sinh of t, or natural log of t, or square root of t, or something that, I guess square root's not too bad because you've got the power rule, but you can kind of see where I'm going with that. Is that what if that function's not really nice? What if it's a secant, for God's sake, right? What kind of function differentiates and gives you a secant? Or more to the point, what kind of a function after you differentiate it and differentiate it again and combine it in this way gives you a secant? Hell if I know, right? And so what we're going to want is a technique that allows us to get away without making the guess. And we have such a technique. So what we're going to do Wednesday, I'll show you a few more examples, more complicated with this undetermined coefficients, let you see how gnarly the systems can get. Like so far, what's the worst system we've had? I think a 2x2, right? There's been like an A and a B we don't know. Yeah, just wait till Wednesday and we'll see how big and horrible they get, which is also why we're not going to do very many of them, because yeah, I'm not going to bother with that algebra. That's definitely where Symbol Lab or the equivalent comes into play. Anyway, so I'm going to go ahead and hit pause on the recording.